Hello everyone, my name is Mike Dolan and I'm the Managing Director of Professional Development at ACI. I'd like to welcome you to this ACI sponsored webinar. We're glad that you could join us for an introduction to tolerance compatibility. For continuing education credit, attendees must purchase the ACI e-learning course titled Tolerance Compatibility, $24 for ACI members and $30 for non-members. Attendees that pass the 10-question quiz in the e-learning course will receive a certificate for 1 professional development hour of continuing education credit. Visit acielearning.org and log in to access the ACI e-learning site. The quiz will be available immediately following the conclusion of the webinar, and a recording will be made available for review within the week. ACI is an approved education provider for the American Institute of Architects, and the e-learning course based on this webinar has been approved for 1 learning unit. Our learning objectives for this webinar are shown on the screen, and they're also included in your handout. And now I'd like to introduce our speaker. Eldon G. Tipping is a fellow of the American Concrete Institute and president of Structural Services, Inc. Is based in Richardson, Texas. A leading authority on tolerances and construction of both on-ground and suspended floors, he was selected by Concrete Construction Magazine as one of the 10 most influential people in the concrete industry in 2005. Elected to receive ACI's Delmar L. Bloom Distinguished Service Award for leadership of ACI Committee 302 floor and slab construction, and elected to the ACI Board of Direction from 2006 to 2009. Eldon is currently a member of ACI's Technical Activities Committee, Tolerance Committee 117 as a past chair, Concrete Floor and Slab Construction Committee 302 as a past chair, and Design of Slabs on Grade Committee 360. Eldon received a bachelor's in architectural construction and a master's of architecture and construction management from Texas A&M University with an emphasis on structural design and management. And with that, I'd like to turn it over to Eldon for our presentation. We'll get the screen switched over here in just a second, and Eldon can take off from there.
Thanks, Mike. Well, good afternoon to each of you. I'm really happy to have the opportunity to share with you developments that have recently come to fruition from ACI 117. For many years, we've recognized a problem with the compatibility between concrete tolerances and those with materials that attach to or are adjacent to concrete. At its root, tolerance compatibility is all about effective communication. And we all know that sometimes what you mean to say is not the way people understand it. There are examples to be found everywhere. For example, in Copenhagen, this notice in an airline ticket office, or in Athens, this notice to visitors. And in Paris, a request that you leave your values at the front desk. And then, of course, in Zurich, one that's a little more entertaining. But the reality is that the only way that the designer has to communicate with the contractor is through the contract documents. And so it's imperative that the designer clearly indicate in the contract documents exactly what the requirements are for the work. The 117 guide to tolerance compatibility actually takes a look at industry standard tolerances for a number of different industries, and then compares those industry tolerances with the ones that are contained in ACI 117, and then follows up by providing recommendations for mitigating those tolerance conflicts as they relate to the work that is either adjacent to or attached to concrete work. The document is divided into a number of chapters. Of course, there's the introduction and then Chapter 2 is for notations and definitions. But then we start talking about tolerance, coordination, and responsibility for that particular activity. The document addresses how one might approach developing a design that is compatible with respect to tolerances for concrete and adjacent materials. The heart of the document is Chapter 5, where we actually look at a number of different areas, a number of different industries that cost the construction industry quite a bit of money. And within each of those areas of interest, look at industry tolerances side by side with ACI tolerances, and then we provide strategies for mitigating the conflicts that occur between the two. The best way to address potential conflicts is during the design phase, where the architect and the engineer can use the recommendations that are in this document to accommodate individual material or product tolerances where they interact or interface with concrete. When tolerance issues are not addressed during design phase, then contractors can actually use the recommendations in this guide to mitigate the conflicts by either pointing them out to the designer and working out an accommodation, or by developing some field fixes. So you might ask yourself, why do these fit-up tolerances actually, conflicts actually exist? Well, the problem is that the American Concrete Institute and other trade and industry standards writing organizations have independently developed different tolerance requirements that are specifically related to their work. And much like the folks in Congress, sometimes these different trade and industry standards and the ACI don't work well together. One of the principal recommendations of this document is to hold a pre-construction tolerance coordination meeting. The attendees should include the owner, the general contractor, the construction manager, the designer, the concrete contractor, and any other subcontractor whose work interfaces with the concrete construction elements. And the idea of the meeting is to allow each of those attending to address any anticipated tolerance compatibility issues that they see between their work and the concrete construction. On most projects, the architect engineer is responsible for coordinating tolerances. You'll find that point made in a number of different sources: ACI 347, ACI 117. The American Society of Concrete Contractors has developed a position statement on that issue, and the ACI Committee 132 on responsibility in concrete construction also takes that position. So we move on to Chapter 4, which is kind of a roadmap to how you might establish tolerance compatibility for your particular documents or for a project. The first thing, of course, is to gather tolerance information. You have a number of different sources listed here. You have to determine the requirements for the particular function of whatever it is that is being studied. And then the architect and engineer should identify what's required for the constructed element. In other words, the outside face of what folks actually see in the finished product. And then, very important, establish a clear protocol for measurement and acceptance of the tolerance feature, component, or assembly. Once you've gathered that information, then you have to evaluate it. Sometimes you'll find that there are multiple tolerances specified for a different component depending on the organization you're talking about. For example, with regard to wood flooring, The Maplewood Flooring Manufacturers Association and ACI differ in the concrete surface quality for the installation. The Maplewood Flooring Manufacturers Association establishes a tolerance of level within 1/8 of an inch in a 10-foot radius for their flooring. ACI is much less stringent than that. Another example is the American Institute of Steel Construction, where the two organizations, AISC and ACI, differ in their location tolerances for anchor bolts and for weld plates. Once you've evaluated, or during the evaluation process, you also have to identify tolerances that are required by the interfacing components that are not consistent with ACI 117. For example, the two that we just talked about previously, AISC and ACI, and then the Maplewood Flooring Manufacturer. Once you've identified those differences, you've got to find an appropriate solution. With regard to the flooring issue, the American Society of Concrete Contractors has issued a position statement which recommends allowing a tolerance in the contract documents for any necessary grinding or leveling. And then, of course, a part of this evaluation process is to investigate how the identified tolerances combine and interact with each other by looking at various scenarios for construction. So you've identified, you've done your research, you've identified or evaluated the situation, and then of course the final, or one of the final steps, is to generate solutions that create compatibility. That might be by using filler materials. It might be by using a design, a flexible design that accommodates the particular tolerance incompatibility that you're dealing with. So again, you might ask yourself, why don't we just specify more restrictive tolerances? Well, you can do that, but the reality is that sometimes that's not the answer. In fact, most of the time that's not the answer. Specifying more restrictive tolerances often, even though it's the easiest way to create compatibility, what you find is that sometimes you can't do it for any amount of money. For example, the AISC Design Guide 22 very clearly states that designers can specify more stringent tolerances, but they need to recognize that sometimes it's unreasonable to disregard the realities of the construction. Well, I would say always it's unreasonable to disregard the realities of construction practices. Chapter 5 is the heart of the document. And what you'll find is for each of the work areas addressed by the document, there will be this information that's shown on the screen. There will be industry tolerances in a side-by-side format. So we will have, for example, AISC formats. Well, let's just go to the next slide and show you. We will have the specific tolerance item, and then the tolerance that appears in the industry document, whatever it may be. In this case, it's the American Institute of Steel Construction, side by side with ACI. And you can see here that there are some areas that match and there are some that don't. And then we will, after identifying those, we will develop some, there's some discussion, and then we will provide a strategy for dealing with it, either from a design standpoint or from a construction standpoint. Embedded plates are a good place to start because the requirements are really quite different. The American Institute of Steel Construction states that for embedded plates, the variation in location has to be limited to the tolerances that are specified in Section 7.13 for the erection of steel, structural steel. Well, you might ask yourself, well, what are the requirements in Section 7.13? Well, there are some of them, and there are some more. So AISC starts by saying, well, you've got a bunch of different requirements for the location of embedded plates. You've also got to deal with what's in 117. And 117 isn't the only document that has tolerances for the location of embed plates. ACI 355 has a state-of-the-art report. Some of these requirements are more rigorous than those in 117. And as stated here, they're judged to be more economical than the consequences of not meeting them. And then, of course, there are tolerances in the precast and pre-stressed concrete construction documents. So what we have is a plethora of tolerances from different industry organizations. And let's see what happens when we get into the field. I mean, essentially what we were looking at was, if you go back here, positioning within 1/4 of an inch. Well, that's a really nice tolerance to achieve until you start looking at the reality of what we've got in the field. Here we have a plate, embed plates. This happens to be in California, but these embed plates have to be erected with a crane. And what we're hoping for is location within 1/4 of an inch in any direction. Well, 117 is a little more lenient than that, but even so, you can see that because of the reinforcing congestion and the fact that the headed studs or the embed attachments to the plates are prefabricated, it's a very difficult coordination issue to get plates located exactly in the field. Another example of the challenges that you see in the field with regard to proper positioning of plates. And then, of course, you've got some combined situations where the concrete construction has embedded plates, and then you've got to attach structural steel to it. In this particular case, you'll notice that the web, the bottom flange of this beam is actually below the bottom of the plate, and actually limited the ability of the weld, or the length of the weld between the connection angle or the connection plate and the embed plate. So the lesson here for the designer or specifier is pretty simple, really. You need to avoid details that require perfection in the field. A very simple solution is to consider the use of oversized plates. How about elevator hoistways? You know, elevator shop drawings show opening dimensions, clear hoist opening dimensions that are very often used by the designer. I wonder how many times the designer actually looks at this note that also appears on the elevator cut sheets, which says that the clear opening cannot be less than the dimensions shown on the drawings. So what you got here is a dimension shown on the drawings that is a minimum 7'7" by 18'4". Well, that's pretty easy to accommodate on a level. But what happens when you have multi-story construction? If you've got an opening that is 7'7" by 18'4" on each level, and the openings don't line up perfectly from one level to the next, then suddenly you've got a clear opening that is much less than the specified. The thing to remember is that there's no tolerance on minimums and maximums. So the designer is well advised to avoid designing to those maximum and minimum tolerances. How about curtain walls and window walls and sliding doors? It's not unusual, particularly for condominium projects, to have window or curtain wall units, window wall units, and sliding doors that actually fit in a framed opening. Well, it looks like it might work real well, except concrete framing deflects. And once that deflection occurs, then you've got a restricted opening for your slider or window wall. Another consideration is curtain wall is typically installed in three-story long segments, and yet at the interface between the curtain wall and the part that has to fit between the concrete, you very often got a detail that has no forgiveness at all. And then this particular part of the assembly is impacted by the distance, of course, between the framed opening and the deflection that occurs once the forms are removed. There's a tolerance on the the height of the floor from the ground. There's a datum established for that. And then, of course, the concrete itself is not going to be perfectly flat. All of those things impact the ability of a slider or a window wall to fit within a framed opening. Thickness of the slab is another issue. So again, the caution for the designer or the specifier is to avoid details that provide perfection in the field. Provide some details that allow for the imperfections that are going to occur. How about column location? I've been in hotel lobbies where I see these numerous columns lined up in like soldiers in each direction. In this particular case, we've got 18 columns in a hotel lobby shown, plan location is shown. Height of each one of these columns is 18 feet. Plan dimension for each column is 24 by 30, and each column has marble cladding. Well, of course, what you want is the outside face of the marble to match up in each direction. So the questions to be considered are, what's the allowable variation in location for each of the columns? What's the allowable variation in thickness for the columns? And then what's the allowable variation in plumb for each of the columns? And then most importantly, how much clearance, after you consider all of those things, how much clearance do you have to allow for attaching the marble and have the face of the marble line up? Well, if you look in ACI 117, you'll find that there is a tolerance for the location of the element, plus or minus an inch in any direction. There's a location for plumb, which does not add to the location tolerances. Both of those have to exist within the 1 inch, the plus or minus 1 inch dimension. And then there is a location or tolerance on the cross-sectional dimension of the element. There's also a tolerance on the departure of the form surfaces from the specified plane over a distance of 10 feet. I've got to tell you here, this is an issue that's being worked on by ACI right now. For the mathematicians in the group, you'll notice that 0.3% of 12 inches is not 3/8 of an inch. We've misplaced the decimal point here. These numbers should be 3%, 2%, and 3% and 2%. But here we have the as-built locations of the various column sections. And just as one, just one example, what we find is that you've got, for the concrete section, for the 18-foot height of the section, there is a plus or minus 1 inch envelope here that the concrete must fit in. And so the marble cladding, the detail for the marble cladding has to accommodate that type of mislocation or out of plumb of the concrete elements in order to have the face of the marble line up. So it's important for the designer and specifier to consider the impact of these kinds of tolerance issues on the end product when they're developing the details. We also look at, in the document, some disability guidelines. Let's take a look at ramps, for example. For the architects in the group, what you'll see here is that there is a maximum slope requirement, or maximum and minimum slope that can be used for ramp lengths of various dimensions. Up to 30 feet, you can use a ramp slope between 1 in 12 and 1 in 16. Well, my experience has been that there is a reluctance on the part of designers to devote more real estate to ramps than is necessary. So what is normally done is that the ramps are designed so that they meet the 1 in 12 requirement. Well, that's a maximum slope requirement that looks good on paper, but it's very difficult to achieve in the field. For example, if the ramp drops below that straight line connecting the two landings, then over in this section, you have a slope that exceeds the 1 in 12 limitation. If you have a ramp that departs on the plus side for a part of the distance between the landings, then this part over here of the actual as constructed ramp would violate the 1 in 12 limitation. And then, of course, this is more normal. You'd have a violation here and here of the 1 in 12 limitation on maximum slope. So the important thing is for, again, avoid designing to maximum minimum requirements. There's no tolerance on maximums and minimums. So the designer really must be very careful to avoid designing to those tolerances, because they're not going to be achieved in the field. There is no such thing as perfection in the field. The impact of time on flatness and levelness is something that has been an issue for a number of years. If you look at a traditional floor surface, there are really a couple of things that are important. One of them is whether or not the inclination of the floor is parallel to that of the design, and the other is whether or not the planar characteristics match those shown on the design requirements. The 117 document addresses the F numbering system in section 4.8.5. It assigns numerical value to the flatness and levelness of these floor surfaces. The flatness number controls the local bumpiness of the floor, measured typically over a distance of 2 feet. The levelness is controlled or developed by looking at elevation differences over distances of 10 feet. The important thing is to remember that the levelness number is impacted negatively by deflection and camber. When you're looking at elevation differences over a distance of 10 feet, then that's judged against a horizontal plane. If you're measuring a cambered or deflected surface, then the levelness numbers that you get will be distorted as a result. Another thing to think about is that concrete is not, well, concrete shrinks with time, about 1/8 of an inch in 20 feet over generally a year or two. But that change in time, that change in volume and profile starts to happen as soon as the concrete starts to lose excess water. This particular situation was a super flat floor, which is a very, very level and very, very flat floor that was not reinforced, and it was saw cut at intervals, and those intervals, after just a period of 37 days, showed this kind of distortion at the joints. So there is a clear, for slabs on ground anyway, there's clear evidence that over time the flatness and levelness of a slab on ground is distorted by the normal drying shrinkage of concrete. We actually did a time study on a practice gymnasium at a university several years ago, and what we did was collect data across the concrete. Was placed in strips vertically as you look at them here, and we collected data intentionally not to meet the requirements of ASTM E1155, which is the standard for governing evaluation of floors using this method. We wanted to look at what happened over time to the concrete. So we collected some data close to construction joints here. 3, 5, and 8 were very close to construction joints. And then we also collected across multiple placements so that we were able to see what happened across the strips after time had passed. Just for example, we looked at measurement line 3, which is very close to a construction joint, and measurement line 13, which was across multiple joints. The first time we collected data was in October 2001, and then this is the same measurement line location tied to a benchmark. So the relative elevation of these two measurement lines is accurate. This measurement line on the left in 2001 was very close to design grade. The measurement line to the right, taken in June 2002, was clearly had distorted because of curling. But look what happens to the flatness and levelness numbers. In October of 2001, 57.8 and 57.5. In 2002, the flatness had dropped to 45 and the levelness to 37. Pretty significant drops in the quality. The measurement lines across the strips, in November 2001, we started out with a 49 and a 28 in terms of flatness and levelness. In 2002, May, just 6 or 7 months later, it had dropped to a flatness number of 26.1 and a levelness number of 22.9. Significant impacts on the impact on flatness and levelness. The 2001 data combined results of FF50 and FL42. In May and June, that had dropped to FF40, FL33. So pretty much a 25% drop in the levels. The lesson here, and the one that has pointed out earlier, as I noted, is in the position paper published by the American Society for Concrete Contractors, is it's important for the designer to specify or recognize that time will impact in a negative way the flatness and levelness of the concrete slab that has been placed. A particular example here is Division 3 and Division 9. Division 3 is what governs the work, the concrete work done by the contractor. Typically, the flatness and levelness are specified using FF and FL. Measurements are specified to be taken within 72 hours, and the test standard is ASTM E1155. Division 9 typically uses variations of the gap below the straight edge, or a level straight edge approach. The measurements are taken when the floor covering, Division 9 covers floor coverings that go on top of concrete. The measurements are generally taken when the floor covering is installed, and there is no standard other than ACI 11710 for measuring floors using the gap below the straight edge. 11710 establishes minimum requirements for evaluation of floors using the gap below the straight edge approach. There is no national standard or standard within ACI 117 for checking levelness using a gap or using the straight edge approach. So what you see is that if the concrete meets what is specified in Division 3, then when the Division 9 work goes into place, sometimes as much as 12 months later, there is a decrease in the quality of the work that is done. So how do you deal with that situation? You know, you got an FF50 that might be put in on day 1, and by the time the Division 9 work is ready to go in, you've dropped to an FF30. So there is a clear problem in this particular area. And the options here are, well, there's several. One of them is to buy an initial flatness that's high enough so that after it's distorted, you've got a flat enough floor or level enough floor to meet Division 9 requirements. Another option is to buy steel, 0.5% of the cross-sectional area of the steel, so that you can continually reinforce the slab and eliminate construction joints. That will pretty much maintain the original profile of the concrete until indefinitely. And then, of course, the last two are by grinding and patching. It just depends on who pays for it, whether it's the concrete contractor or the flooring contractor. All of these things have and the reason this has been an issue over the years is that there's money involved in each of these solutions. The question is which solution you choose. The contractor, if he gets a set of drawings with these discrepancies in them, has some options. He can exclude it in his bid. Fat chance there. Making the general contractor and the construction manager aware of it, make the architect and engineer aware of the dispute. Might suggest a specification change. One of the things that you could do was have the flooring contractor include in his bid whatever surface preparation is required to make the floor suitable for the covering based on floor flatness requirements that are in Section 3300, the cast-in-place concrete work. The lesson for the contractor is to recognize when you look at the drawings if there are inconsistencies in the specifications, they need to be identified and addressed quickly. For the designer, hopefully you will avoid producing documents that get you into that boat. Reinforcing placement, another issue. You know, we looked at an earlier situation with embedded plates. Well, you can imagine that there are other situations where reinforcing placement is an issue. Looks pretty nice here, doesn't it? This is a post-tension situation where the designer has provided proper clearance for all of the reinforcing and post-tensioning that needs to run through this column intersection here. One thing to note is that, you know, this vertical dowel and this vertical dowel don't line up. So it's not always practical for a designer to assume just because on paper there's enough room to get the reinforcing through a column or a beam intersection. You know, the reality is that sometimes in the field these reinforcing elements are offset a little bit, so the straight path through the joint is not going to be there. Things get a little more congested when you get to the edge of this particular building and you have all the confinement reinforcing that's required. This is what's known in the industry as trying to put 10 gallons into a 5-gallon bucket. Interesting as much as anything is the challenge that the contractor faces in first getting the reinforcing in there, and second getting concrete around all this reinforcing. The lesson for the designer and the specifier: avoid details that require perfection in the field. You know, coordination and accommodation of tolerance conflicts is something that everybody needs to deal with. It is a subject that costs the construction industry hundreds of thousands of dollars every year. And they're the types of things that can be dealt with by a knowledgeable designer, a knowledgeable contractor, and more than ever, more than anything, the willingness of those two entities to talk to each other before the ox is in the ditch. So how you handle this, I would say the devil is in the details. I thank you very much for your attention. If you have any questions, I'll be glad to entertain them at this time.
Okay, thank you, Eldon. Very interesting presentation. We have a few questions that are coming in now. I remind you to type your questions in the question chat box if you have some that you'd like to have answered by Eldon. The first one is, we have a listener that noted that the conflicts between the specs exist at bid time and at the pre-construction conference. So what do you suggest to be resolved without the owner having to fund a change order? Or do these almost always result in some sort of a change order that someone's going to have to pay for?
Well, if it's a hard bid job, then if it's pointed out prior to the bid during a pre-bid conference, then the designer has the opportunity to develop a flexible detail that will deal with the issue. Other than that, if it's a hard bid job, if you're actually you bid the plans and the specifications and you've identified these conflict issues, then the only approach really is to address it in a pre-construction tolerance conference as is recommended by the document, and that will bring the issue to the table and develop a resolution which may be a cost item to the contractor or to the project, but again, it may not. I mean, there are often the slotted angles, and there are a lot of modifications of details that can be made. If they're made before the elements are fabricated, then there's not necessarily going to be an add to the job. If you're far enough down the road that that you already have the material on hand, then it becomes an issue.
Okay. I'm not sure if you'll be able to answer this one based on 117 document, but maybe some of the other committees you're in. One person asked if the use of macrofiber and slabs helps with maintaining FF and FL values.
Well, to the extent that high dosage macrofibers, if you were talking about synthetic macrofibers in probably the, close to 6 or 7.5 pounds per cubic yard range dosage, you can typically extend joint spacing, which helps with respect to maintaining the original profiles. There's a school of thought. One of my partners came up with this, and I tend to agree with him, that high dosage synthetic fibers make the concrete a little more less brittle, so that it doesn't have the effective section modulus that would be necessary to generate a lot of curl. So it really depends on the dosage, I think, and the particular location. I mean, there are some parts of the country where curl is not a particular problem. Areas being maybe coast, close to the coast, the Gulf Coast, Houston, Galveston, New Orleans, areas with real high humidity. If you don't have significant differential drying of the concrete, then you don't have to deal too much with curl.
Okay. Another question was that you stated that FL measurements can be influenced by deflection and camber. Can the FF measurements also be affected?
A little bit, but generally not a lot. If you think about it, the flatness number is generated by looking at changes in slope over a distance of 2 feet. So if you look at deflection, let's say we've got a suspended floor that maybe we're talking about a 30 by 30 bay. So you've got a curvature that changes maybe from, let's assume, a straight line between two columns to a curvature of maybe 3/4 of an inch drop. So you've got a 3/4 inch sag between those columns. Well, if you're looking only at a 2-foot long section of any part of that curve, then the difference in slope, or the difference in the change in slope over that distance is pretty small. So I would say, yeah, there's probably a minor impact, but it's not as significant as the impact of deflection on levels.
Okay. Another question, how does the concrete subcontractor protect itself from these conflicts? Once the conflicts are found in the field, they're generally expected to fix at our expense. Is just taking the time to find those conflicts and get them resolved early?
Well, that's the $24 question, or maybe more expensive than that. It's always easier to keep the ox on the road than it is to get him out of the ditch. So, yeah, identifying, I can't tell you how important it is to have an effective pre-construction tolerance conference before everybody starts, and to come to that meeting prepared to discuss the various issues. I mean, most contractors if you've been in business any amount of time, most contractors are going to know where the issues are that cost them money, and they're going to know where the things happen that they end up paying for, even though it may not ultimately be their fault. So the time to address those issues, really for everybody, for the benefit of the job, is before you actually start. So all the way up and down the line, I think it's important for the people that are involved in the job to insist on having an effective pre-construction tolerance conference to discuss these items.
Okay. I'm going to paraphrase this question a little bit, but this person is saying that they find that the GC and the CM really don't fully grasp the time restraint on testing FF and FL for floors, and that they don't recognize the 72-hour testing window. He's wondering if ACI 117 is going to provide any further language in the future regarding that the manual straight edge method is only truly viable and accurate shortly after placement.
The 117.10 does place the 72-hour limit on the straight edge measurement, as well as flatness and levelness testing using the F-numbering system. That 72-hour limitation is already there.
Okay. I believe this was more of a comment than a question. Somebody commented that you have to bid with clarification that you will bid the ACI 117 tolerances and get it into the contract. Another person stated that the best way is to be more specific and clarify what tolerances are included in your proposal. Do you find that doing those two things helps quite a bit, or do people still get into trouble?
I don't know that you need to specify that that's what you're doing, because that's generally a part of the contract documents. If the contract documents specify the use of ACI 301, which they typically do, then ACI 301 incorporates ACI 117 with regard to tolerances. There's some defaults in there, but essentially 117 is, if you specify or see that 301 is specified, then 117 goes along for the ride, whether it's mentioned specifically or not. I think that there are, and this, how do I say this? I think that there is a general lack of attention in the design, on the design side of the fence, with regard to this whole issue. I truly believe that that this document will be a great resource for designers, because it's the first time that we provided them with a resource that identifies specific fit-up issues that occur all the time on virtually every project that involves the materials involved, that are discussed. So I mean, I guess you could say it's great insomnia material, but the reality is, I think it should be pretty interesting reading for anyone who wants to do a better job for their clients.
Okay. One other thing I thought maybe you could discuss for just a few minutes was whether you see any efforts among the different tolerance writing groups, say the flooring manufacturers and the concrete floor slab concrete contractors, or the ACI. Is there any efforts going on? Do you see more efforts to harmonize the tolerancing compatibilities, or is there anything going on that front?
Efforts, yes. Progress, no. We've got, we've got some joint committees between, ACI and AISC, for example, addressing specifically, we're looking at some of the anchor bolt, or anchor rod tolerances that, trying to develop a way to make what they have developed with, with what we can do, and there are some industries that are, develop documents really just to cover their own backside, and then there are others that are, well, for example, the ACI goes through the standardization process, and we get users and owners and designers, pretty much everybody involved in the process, and not to throw rocks at the steel industry, but that particular approach, I mean, if you look at it, there is no specific elevation tolerance on the erected steel frame. I mean, other than base plate elevation plus or minus an eighth of an inch. And then after that, everything is fabrication tolerance. And so you've got just a bunch of sticks and whatever, steel pieces that you fit together, and however they fit together is how they fit together. Now, I guess you could just stack the tolerance and the fabrication tolerances on top of each other and come up with an envelope, but that's not a very realistic way of approaching, approaching the tolerance issue. So I would say there are some industries that really look more toward what they want and need ideally, and don't really spend a lot of time thinking about other requirements. It's it's what I said earlier. It's kind of like the folks in Congress now, that they're more interested in themselves than in coming up with something that works. So they don't play well together. And I think at some point that needs to happen. And I think this document is a good start to developing that dialogue, and providing folks with an opportunity to ask the questions that need to be asked, and to maybe see if there's not some way to arrive at a kind of a happy meeting ground between the various materials.
Okay. I think we have time for just one more quick question here. Let's see, one of our listeners had asked if the new edition of 117 is going to revise the top of foundation levelness tolerance for support of masonry. It says the 2010 edition did not recognize the tighter tolerance requirement that existed in earlier editions.
The new 117, or the next cycle of 117, will take that, we'll take a look at that particular issue. I don't know where the committee is going to fall with regard to changing it. I would suspect that it probably revert to the tighter tolerance that was originally used, if it can be reasonably achieved. But that's a committee decision, and I'm on the committee, but I can't speak for the committee.
Right. Okay, well, it's coming up on 1 o'clock here, so I'm going to remind everybody to please fill out we have a brief survey, a brief feedback survey that will be coming out shortly after you sign off, either by email or in a pop-up window. And if you're looking for continuing education credit, be sure to register for the course and take the quiz online at acielearning.org. The quiz should be available now, and a certificate will be emailed to you immediately upon successful completion of the quiz, so you'll be able to get your certificate right away. And I especially want to thank all the attendees for showing up, and especially Eldon for giving us a presentation on such a timely topic and such an important one that still has a lot of good work yet to be done, but certainly making great strides in helping designers and constructors and owners come together on some of these issues and getting them out in the open and finding good solutions that work well for everybody. So that will conclude our webinar, and I hope you enjoyed it. Thank you very much.